Combinatorics, Lecture 7, Inclusion-Exclusion Principle. Let us recall the rule of sum, so one of the basic counting principles, the rule of sum, and let us recall it in its sets-theoretic version. Let x and y be two finite sets. Assume that their intersection is empty. Then the rule of sum asserts that the cardinality of the union of x and y is equal to the sum of the cardinalities of x and y. More generally, if we have a finite collection of pairwise disjoint sets x sub I, where I runs through some finite indexing set capital I, then the cardinality of the union of these xi's equals the sum of the cardinalities of each individual xi. And here it's very important that these sets are pairwise disjoint. And the motivating question for today is what happens if the intersection of x and y is non-empty, respectively if the xi's we start with are not pairwise disjoint. And the aim of today's lecture is to answer this. So let's start with a general case of two sets. So in the case when two sets x and y are not disjoint in general, so in the case of two sets, it's not difficult to see how the general formula should look like. Proposition: let x and y be two finite sets without any other restrictions. Then the cardinality of the union of x and y is equal to the cardinality of x plus the cardinality of y minus the cardinality of the intersection of x and y. Proof: if we count first all elements of x and then all elements of y in some order, then we may notice that each element of the intersection is counted exactly twice, once as an element of x and another time as an element of y. Therefore, we need to subtract the cardinality of the intersection from the sum of the cardinalities of x and y to get the cardinality of the union. And this completes the proof of this proposition. So, for two sets, the general formula looks quite easy. Let's go to the case of three sets. So, assume that we have three finite sets, x, y, and z, without any further restrictions. Then we have the following formula. The cardinality of the union of x, y, and z equals to the cardinality of x plus the cardinality of y plus the cardinality of z minus the cardinality of the intersection of x and y minus the cardinality of the intersection of x and z minus the cardinality of the intersection of y and z plus the cardinality of the intersection of x, y, and z. Proof: again, like for two sets, let's count elements of x, then elements of y, and then elements of z in some order. And from the previous case, we know that we overcount the intersections. So we need to subtract the intersection of x and y, we need to subtract the intersection of x and z, and we need to subtract the intersection of y and z because we count them twice. But when we subtract these three things, the elements of the intersection of x, y, and z get subtracted 3 times, while in the original counting they were counted 3 times. So they just disappear. We have to put them back in order to obtain the cardinality of the union of x, y, and z. So this proves proposition in the case of three sets. And now we can formulate the general case, and that's the theorem which is called the Inclusion-Exclusion principle, or the principle of inclusion and exclusion. For arbitrary finite sets xy, x2, and so on, xk, we have the following. The cardinality of the union of x1, x2, and so on, xk equals the sum over all m from 1 to k, then the sign minus 1 to the power m plus 1, and then we have another sum which now runs over all indices I1, I2, and so on, Im, where I1 is greater than or equal to 1, I2 is greater than I1, and so on. IM is greater than IM minus 1, and IM is less than or equal to k. And we take the cardinality of the intersection of xi1, xi2, and so on, xim. Alternatively, we can write the same formula in the following form. The cardinality of the union of x1, x2, and so on, xk, equals the sum over all subsets I in K underlined. Then we have the scalar sign minus 1 to the power the cardinality of I plus 1, and then the cardinality of the intersection of all x sub s, where s runs through I. Let's make the following remark. By convention, the intersection over an empty set of indices is empty. So there is a small difference between these two formulas. In the second formula, there is a possibility that I is an empty set, but then the corresponding summand is 0 because the corresponding intersection is empty, so it has 0 elements. Proof. To prove the inclusion-exclusion formula, we proceed by induction on K, on the number of sets. The basis of the induction, that's the case K is equal to 1, is trivial. And in fact, we already checked the formula for K is equal to 2 and K is equal to 3. For the general induction step, we assume that our formula is true for some K, and we try to prove it for K plus 1. Let us denote by Y the set x1 union x2 union and so on union xk. Then x union with xk plus 1 is exactly the union of x1, x2 and so on all the way up to xk plus 1. Since we already did the case of k is equal to 2, the cardinality of the union of y and xk plus 1 equals the cardinality of y plus the cardinality of xk plus 1 minus the cardinality of y intersection with xk plus 1. And here y is the union of k sets, so we can apply the inductive assumption, and so this cardinality of y is given by the right-hand side of the inclusion-exclusion formula for this particular k by induction. Therefore, in order to prove the inductive step, we only need to check that the terms on the right-hand side of the inclusion-exclusion formula for k plus 1, which contain x sub k plus 1, give exactly the cardinality of x sub k plus 1 minus the cardinality of the intersection between y and x sub k plus 1. Of course, the term the cardinality of x sub k plus 1 is manifestly in the formula. It corresponds to a singleton subset for the index equal to k plus 1. And the remaining terms add up to the following formula. So we have the sum over all m from 2 to k plus 1. We have the sign minus 1 to the power m plus 1. And then the sum over all indices I1, I2, and so on, im minus 1. And then im, and this index is equal to k plus 1 because we only take terms where xk plus 1 is present. And then we have the cardinality of the intersection of the corresponding xij's. For I between 1 and k, let us denote the intersection between xi and xk plus 1 by zi. Then our intersection in the formula can be written as the intersection of zi1, zi2, and so on, zim minus 1. And so our formula becomes the sum over all m from 2 to k plus 1, minus 1 to the power m plus 1, and then the sum over all I1, I2, and so on, im minus 1, and then the intersection between zi1, intersection zi2, and so on, intersection zim minus 1, and we take the cardinality of this set. Here we can replace m by m minus 1, because we intersect m minus 1 sets, and note that this means that our sign will change, so we have to move minus 1 outside of the formula. So we will get sum over all m from 1 to k, minus 1 to the power m plus 1, and then the sum over all I1, I2, and so on, im, and then the intersection of zi1, zi2, and so on, zim, and we take its cardinality. By the inductive assumption, this gives us exactly minus the cardinality of the union of zi1, zi2, and so on, zik. This should be k, of course. But, of course, this union, by definition, is equal to y intersection with x k plus 1, because intersection distributes over the union, and this exactly implies our formula. So this completes the proof. We can also give an alternative proof for the inclusion-exclusion formula, which works as follows. Let's take some element a in the union of x1, x2, and so on xk, and let us determine the number of times a is counted on the right-hand side of the inclusion-exclusion formula. We want to show that it is counted exactly once. So let us assume that a belongs to exactly R of our sets, say to the sets xi1, xi2, and so on xir, for some indices i1, i2, ir in the order between 1 and k. Then a is counted r times in the intersections over singletons, and r equals to r choose 1. So it is counted once as an element of xi1, it is counted once as an element of xi2, and so on. Exactly r times in the intersections over singletons. Then we observe that a is counted minus r choose 2 times in the intersections over two-element subsets. So when we take some xi sub p and intersect with some x sub I sub q, then a is counted there, and of course that intersection comes with the minus sign. So we get minus r choose 2 times from two-element intersections. Similarly, a is counted r choose 3 times in the three-element intersections, and so on. If we add everything up, we get that a is counted r choose 1 minus r choose 2 plus r choose 3 minus and so on plus minus 1 to the power r plus 1 r choose r times. To understand what this gives, let us apply the binomial formula to the expression 1 minus 1 to the power r, and this is of course equal to 0. So if we apply binomial formula to the left-hand side here, we get the sum over all I between 0 and r, minus 1 to the power I, and then r choose I, and this is equal to 0. And here we can move everything where index is different from 0 to the right-hand side, and get that 1, that's the value of the expression where I is equal to 0, is equal to the sum over all I from 1 to r, minus 1 to the power I plus 1, r choose I. And that's exactly our long sum here at the beginning. So each element a is indeed counted exactly once on the right-hand side of the inclusion-exclusion formula. Let us see how one can apply inclusion-exclusion formula to solve combinatorial problems. Example 1. How many positive integers between 1 and 2025 are divisible by neither 2 nor 5 nor 7? Solution. Let us introduce the following sets. First, the set omega, which contains all integers between 1 and 2025. Then the set A, which contains all elements in omega which are divisible by 2. The set B, which contains all elements in omega which are divisible by 5. And the set C, which contains all elements in omega which are divisible by 7. We know that the cardinality of omega is 2025, and our problem asks to determine the cardinality of omega minus the union of A, B, and C. And this, of course, gives us 2025 minus the cardinality of the union of A, B, and C. So we need to compute the cardinality of the union of A, B, and C, and we can do this using the inclusion-exclusion formula. So we use the inclusion-exclusion formula and have that the cardinality of the union of A, B, and C equals the cardinality of A plus the cardinality of B plus the cardinality of C minus the cardinalities of the two set intersections and then plus the cardinality of the intersection of A, B, and C. Now let us note that A intersection with B consists of all elements in omega which are divisible by 10. Elements of A are divisible by 2, elements of E are divisible by 5. 2 and 5 are prime numbers. If something is divisible by 2 and 5, it is divisible by 2 times 5, which is 10. Similarly, A intersection with C consists of all elements of omega divisible by 14, and B intersection with C consists of all elements of omega divisible by 35. Finally, the intersection of A, B, and C consists of all elements of omega divisible by 70. 70 is 2 times 5 times 7. Next, let us recall that we have the floor function, which has as an input a real number x, and it outputs the maximal integer which doesn't exceed x and which is denoted in this way. So for two positive integers k and m, the cardinality of the set of all positive integers between 1 and k which are divisible by m is clearly given by this floor function applied to the ratio k divided by m, because elements divisible by m are m, 2m, 3m, and so on, and between 1 and k, that's exactly the floor function of k divided by m elements, which we get in this way. Now we compute the cardinality of A, that's a floor function of 2025 divided by 2, this is 1012. The cardinality of B, that's a floor function of 2025 divided by 5, that's 405. The cardinality of C, it's 2025 divided by 7, that's 289. The cardinality of A intersection with B is 2025 divided by 10, the floor function, that's 202. The cardinality of A intersection with C is the floor function of 2025 divided by 14, that's 144. The cardinality of B intersection with C is the floor function of 2025 divided by 35, that's 57. And the cardinality of the intersection of A, B, and C is the floor function of the 2025 divided by 70, that's 28. And now we can insert all these numbers into the inclusion-exclusion formula and compute the final answer. So we have 2025, that's the cardinality of omega, minus our inclusion-exclusion formula, which is given by 1012 plus 405 plus 289, minus 202 minus 144 minus 57, and plus 28. This gives us 2025 minus 1331, and the final answer is 694. Example 2. Determine the number of surjective functions from a set with k elements to a set with m elements, where we of course assume that k is greater than or equal to m, because otherwise the answer is 0. Solution. Let x be a set with k elements, and let y be a set with m elements. Let f from x to y be a function. To construct f, we can choose the value of f independently on each element of x. Each such value is an element of y, so we have m options for each value, and x has k elements, so we need to make k choices. So by the rule of product, we get that there are exactly m to the power k functions from x to y in total, and the set of all functions from x to y is usually denoted by y to the power x, and we just computed that the cardinality of the set of y to the power x equals cardinality of y to the power cardinality of x. For any subset z of y, the set z to the power x is naturally a subset of the set y to the power x. This should be x. Let us denote by surjective from x to y the set of all surjective functions from x to y. Then, the set of surjective functions from x to y equals the set of all functions y to the power x minus the set omega, which is defined as the union over all a in y. We take y, we subtract a, and we take to the power x. So this means all functions whose image is in y minus this element. So the number of surjective functions from x to y equals m to the power k minus the cardinality of omega. Omega is a union, so we can use the inclusion-exclusion formula to determine this cardinality. So by the inclusion-exclusion formula, the cardinality of omega equals the sum over all non-empty subsets R in Y minus 1 to the power the cardinality of R plus 1, and then the cardinality of Y minus R to the power X. Using our formula for the total number of functions, we get that the cardinality of omega is equal to the sum over all non-empty R in Y minus 1 to the power the cardinality of R plus 1, and then the cardinality of Y minus R to the power the cardinality of X. And let us recall that a set with m elements has m choose I subsets with I elements. So we can rewrite the last formula as follows. The cardinality of omega equals the sum over all possible cardinalities I from 1 to m minus 1 to the power I plus 1, that's this factor, then m choose I, and then this factor m minus I to the power k. And now we can plug this back into our formula and get that the number of surjective functions from x to y equals the sum over all I from 0 to m minus 1 to the power I, m choose I, m minus I to the power k. That's our final answer. Example 3. How many permutations of n underlined have no fixed points? Solution. Let us recall that the set of all permutations of the elements in n underlined is denoted by s sub n and has cardinality n factorial. For any subset x of n underlined, let s sub n upper x denote the set of all elements sigma in Sn, which fix all elements in X pointwise. Let omega be the union of all S sub n upper I is a singleton subset, over all I in N underlined. So to solve our problem, we need to determine the cardinality of Sn minus omega, and this is clearly given by n factorial minus the cardinality of omega. And since omega is a union of something, we can use inclusion-exclusion formula to determine the cardinality of omega. So, for any subset x of n underlined, the intersection of s sub n upper I over all I in x equals, of course, s sub n upper x. And S sub n upper x, the cardinality of this set is equal to n minus the cardinality of x factorial, because elements outside x can be permuted arbitrarily. Elements of x must be fixed, while elements outside x, there are no restrictions, just a permutation. And so we use the inclusion-exclusion formula and get that the cardinality of omega is equal to the sum over all non-empty x, which is a subset of n underlined, and then we have the sum and minus 1 to the power cardinality of x plus 1, and then the cardinality of s sub n upper x. And since we know what the cardinality of s sub n upper x is, we can write it as a sum over all x non-empty subsets of n underlined, the sign minus 1 to the power the cardinality of x plus 1 times n minus the cardinality of x factorial. Again, we see that our summands depend on the cardinality of x rather than on x, so we can rewrite this sum, and if we fix the cardinality of x as k, then there are n choose k subsets of n underlined of cardinality k, so we can rewrite our formula as follows. The cardinality of omega equals the sum over all I from 1 to n minus 1 to the power I plus 1, n choose I times n minus I factorial. So here there is some cancellation. We can plug it back into our formula n factorial minus the cardinality of omega and get the final answer given by n factorial times the sum over all I from 0 to n minus 1 to the power I divided by I factorial. And that's the final answer to this example. Some additional problems and questions at the end. Problem question 1. Check with all details that the inclusion-exclusion formula agrees with the special cases k is equal to 2 and k is equal to 3, how was stated in the beginning of the lecture. Problem question 2. Determine the number of words of length 20 over the alphabet A, B, C, D that contain all the letters. Problem question 3. How many permutations of 5 underline satisfy the condition that I appears neither in position I nor in position I plus 1? Here, the position I plus 1 should be understood as 1 if I is equal to 5, so it takes things modulo 5. Problem question 4. How many permutations of n underlined have at most 2 fixed points? And problem question 5. How many non-negative integer solutions to the equation x1 plus x2 plus x3 is equal to 10 satisfy the conditions that none of the xi's equals 3? Thank you very much and see you next time.